it's actually pretty staggering to think about this, right? This says that whatever I do in the universe, whatever I do, I can't create or destroy energy. Okay? Doesn't matter. On the scale of supermassive black holes and the centers of galaxies, whatever they're doing, they're still obeying this law, this universal law of conservation of energy. They're not creating or destroying energy. Their energy is just being shifted around from these different categories, from kinetic to potential and back, and then maybe some of it is becoming heat. And all over the entire course of history of the universe, we still have this zero. We don't have any evidence for energy just springing into existence without it coming from somewhere, without it being just transferred from one place to another. So again, like I said, I think the analogy or the example I gave you in class was the way that you got to class, or the way that you got to the review session today was you ate some food, right? That food was produced by the Earth in some way that we can trace back to the sun, which we can trace back to the gravitational collapse of the solar system, which we can trace back to all the way back to the beginning of the universe. Yeah? Delta mu initial is heat. Under that it says usually it's referring to heat or energy lost to non-conservative forces.
What about the Big Bang?
What's that?
What about the Big Bang?
That's a good question, Michael, but it's philosophical, so I'm not going to get into it. So the idea, right, is that there must have been some energy there, to begin with at the beginning of the Big Bang, and that energy, is also still here. What causes it before that? What is the sort of negative potential that causes the actual, inflation of the universe prior to that, the Big Bang? We could talk about it for ages. Not going to not in a review session. All right. So if I have just conservative forces, by the way, and I have some potential energy function which is dependent on space. Then I can find the force from my function for potential energy. And I can find that by taking a partial derivative of my potential energy function with respect to x, multiplying that by I hat, plus partial u, partial y times j hat, plus partial u, partial z times k hat, and then there's a negative sign out in front. And so that's basically saying that the force is acting opposite the direction of changing potential energy. So take, for instance, again, the example of a ball dropping through the air, right? A ball has large gravitational potential energy at the top of its flight, and it has smaller gravitational potential energy at the bottom of its flight. The force is acting downwards, right? And so the increase in gravitational potential, though, is upwards, right? So if I want to increase gravitational potential, that's upwards. The force is acting downwards, right? So they're opposite each other. That's why we have this negative sign out in front of this. And hopefully everybody remembers, I'm not going to go through it again, partial derivatives, right? If I have a function of more than one variable, you treat all the other variables as though they're constants, right? And you just take the derivative with respect to that one variable. I'll do one quick example. So if I have a function of x and y, which is equal to x squared y, and I want to take the partial derivative of f with respect to x, that just becomes 2xy. If I take the partial derivative of f with respect to y, that becomes x squared. Right? I just treat the other variable as though it's a constant when I'm taking the partial derivative. All right. So that's what this backwards 6 basically is saying. This backwards 6 symbol. It's really it's a partial derivative. Okay. I'm going to go to the new page. All right. So, another essential topic that you must understand is momentum, which is a vector. So, when we talked about work, kinetic energy, potential energy, all of those things are scalar functions. Okay? They're all scalars, or scalar quantities, right? They have units of joules. Joules is energy. Energy doesn't have a direction. Okay? So those are all scalars. But momentum has some direction. All right. So momentum is defined as this p vector, which is equal to m times v, the mass times the velocity of that object. Right. Alternatively, we can also relate some of the forces to momentum. Some of the forces is equal to minus, or excuse me, it's not equal to minus, it's just equal to plus dp dt. I actually found that, that was a mistake on one of the previous, that was a mistake on one of the previous equation sheets that I gave you on exam number 2. It said minus dp dt, it should be plus dp dt, by the way. It should just be equal to dp dt. All right. And then we also had impulse, which is given by this j vector, which also has units of momentum. And generally, that's an integral from t1 to t2, from some time 1 to some time 2, of the sum of the forces integrated over time, dt, which is also equal to p2 minus p1. So, some change in momentum. So if I exert some force on some object, and I exert some force over some period of time, it changes that object's momentum. And as a result, it's going to change its velocity. Right? It doesn't change its mass, it's just changing its momentum. And so the only thing it can change is the velocity. All right, so that's what I was talking about when I said say impulse. So we had an example problem, for instance, or I shouldn't say an example problem. We had a problem on an exam that a lot of people had trouble with, where a pitcher throws a ball towards the batter hits the ball back with the same magnitude velocity but in the opposite direction. And the question was, which one delivers more impulse to the ball, right? So the pitcher has to exert some force over some period of time in order to get the ball up to some velocity, traveling, I think it was at 40 meters per second, towards the batter, right? And then the batter hits the ball with the bat, right? And the ball comes backwards with 40 meters per second in the opposite direction, right? And so the point is that the impulse is greater for the batter because although the batter may have been in contact with the ball for a shorter period of time than the pitcher was when the pitcher threw with his hands, the force was much greater, right? And I know that because the change in momentum for the pitcher, it went from having momentum is equal to 0, right? Because the ball stops, it has no velocity to begin with when the pitcher starts throwing the ball, and it has some velocity traveling towards the batter, right? So it's that change in momentum is the mass of the ball times 40 meters per second, right? And then when the batter hits it, though, he hits it back in the opposite direction, and it goes back in this direction with velocity of 40 meters per second. The change in momentum is 40 meters per second times the mass of the ball going in this direction, minus 40 meters per second times the mass of the ball going in the opposite direction. And so the change in momentum would be 80 meters per second times the mass. Right? So the change in momentum is larger for the batter than it is for the pitcher, and therefore the impulse would have been larger in that case. So it's delta P that counts, not just the amount, the magnitude of the force and the amount of time during contact makes a difference, but it's also, you also need to think about it in terms of some change in momentum. All right, so this is if we have particles. So this is if we have just sort of individual particles. But if we have some system of particles, where there's more than one mass, or we have more than one object, not just particles, there's a momentum to the system, which is m1 v1 plus m2 v2 plus m3 v3 plus etc. Right? And that's the same as saying the total mass in the system, big M, times some v of the center of mass, where m is equal to m1 plus m2 plus 3 plus that. Okay. And so we introduced this idea of the center of mass. And I realized I didn't put center of mass in my notes, but I can do it right now. So the center of mass, right? The R for the center of mass is just given by M1 R1 plus M2 R2 plus M3 R3 plus dot 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 over M1 plus And so this is a vector giving us a position, and it's essentially giving us the average position of all the mass in the system. Right? So the average position of all the mass in the system is given by the summation of these masses times each of their vector positions divided by the total mass. Okay. Right, and that's the other point about this. When you're choosing, when you're deciding to calculate the center of mass, thank you for pointing that out. You can choose any origin. So what that means is I can, wherever I want to say r is equal to 0, I can put that wherever I want. Right. And that makes my calculation a lot easier sometimes, because then what that does is it eliminates the term on the top of that equation. So on the top of that numerator of that center of mass equation, it might eliminate a term, because I can put one of my masses at r is equal to 0. Okay? So that simplifies things a lot when you do calculations out. Thank you for pointing that out. It's just, yeah, if I have two masses, right, and if I just have two masses and I want to find the center of mass, right, the center of mass is going to be somewhere in between, right, I can treat one as being at 0, and then have the other one, right, and there's still a contribution from both masses in the sense that they're both going to be in the denominator, okay, so it's not like I've completely eliminated that mass from consideration, it's still going to be in the denominator. So it doesn't matter what coordinate system you use when you're figuring out center of mass. You can choose your 0 point, the same way that we can choose our 0 point for gravitation potential energy. I'm sorry? It doesn't change when you have 3 masses. You can still choose your 0 point wherever you want. You can set it up however you like. You can put the 0 point wherever you want. Put the 0 point at Mercury if you want. You can put the 0 point at the center of the galaxy. I don't care. You know, if you're going to end up with the same answer in terms of the center of mass, regardless of where you point your 0 point. Right? As long as you're consistent about making sure that you use the same 0 point for the vector distance R1, or the vector displacement R1, R2, R3, or vector position for each of the masses, right? So you have to make sure you use the same 0 point. You can't switch 0 points as you go from mass to mass to mass, but you have to stick with whatever one you choose. But you can choose whatever you want. Okay, so when we have a system of masses like this, we have situations where we have conservation of momentum. The conservation of momentum happens when we have no external forces. And so that basically tells us that the initial momentum of the system is equal to the final momentum of the system. And that's true of all collisions, by the way. And so that's true when we have no external forces, right? So we also said up here, right, the sum of the forces is equal to dp dt, right? That's also equal to mass times acceleration, right? If there's some acceleration, then v is changing, right? If there's v is changing, then we have some change in momentum, right? So if there's some force, then we have some impulse, and there's a change in momentum, and so we don't have momentum conserved. But in the system, in a situation where we have only, we have no sum of external forces, so the sum of the external forces is 0. Just consider the internal forces of the system, things acting against each other, then the conservation of momentum of that system gives us the initial momentum is equal to the final momentum. Right? And so it's important, and this is something that tripped people up on the exam, and I'll mention it again with the problem with the billiard balls, right, where they're colliding. That's a collision in 2 dimensions, right? So we can use conservation of momentum for a 2-dimensional collision, but we need direction information because this is a vector equation, right? I have in 2 dimensions, right? I can't just say